Swayam Prabha. Digital India. Educated India.
Hello, just continuing what we were discussing, the general form of Euler-Lagrange equations for an integrand containing y and its derivatives up to n. Then we wrote the Euler-Lagrange equation, the boundary conditions. Let us look at that. So, we have now an integrand that depends on y, y prime, y double prime up to y nth derivative. Then we got this equation, Euler-Lagrange equation. That is a single equation, one equation will be there, and you see how we have alternating sign coming, because I goes from 0 to n in steps of 1, 0, 1, 2, 3 up to n, and the sign will be alternating. I equal to 0, it will be a positive sign, I equal to 1, negative sign, I equal to 2, positive sign, and so forth. And then if you look at this, this is how many times you take the derivative, and this is with respect to what you take the derivative of the integrand y f y I, that means that I equal to 0, that will be f y itself, y 0 is y itself, y 1 is like y prime, y 2 is y double prime, and so forth, and same number of times you would have to take the derivative. That is how we get the Lagrange equation, by summing them all up. And here we have the boundary conditions. How many boundary conditions are there? There are n boundary conditions, because you have to do j equal to 1 to n. So, if you have up to n derivatives, you will have n boundary conditions. If you have n equal to 2, then you will have 2 boundary conditions, and so forth. So, if you look at this, this is a little intricate, because we are doing I equal to j to n summation, okay, and if j equal to 1, then you will do I equal to 1 to n, right. When j equal to 2, 2 to n, and so forth. The number of terms will be n when you take j equal to 1, that is the number of terms here will be n terms. When it is 2, you will have 2 to n, so n minus 1, and so forth. Here you will have n terms in the boundary condition, and here it will be j minus 1, j equal to 1 means it will be just h, okay. And then when this is there, we will have n minus 1 terms, okay. Finally, when you have j equal to n, you will go from I equal to n to n itself, so you will have only one term, right. Accordingly, if you go to j equal to n, this will become h n minus 1, that is you have to take h derivative up to n minus 1, okay, and that is how all these terms will come. If you do it for 1 and 2, that we checked just a little while ago. For the 3, we suggest that you work it out, so that you can verify that this is valid, okay. But in engineering, normally you will not have things beyond second derivative, or even physics for that matter, unless you go to very complex problems, you will not have more than second derivative. So, understanding of second derivative is important, but you can also go ahead and understand up to n derivatives what happens. Once again, this is our most general form. This is the general form of a calculus variation problem involving only one function y, but n derivatives, okay. Now, let us go to a case where we have our functional which goes from x1 to x2, whereas this integrand now depends on two functions, let us say y1 and y2. So, both of which we have to make them as variables. There could be problems where, which we will see definitely in structural optimization, where there could be multiple functions that you need to minimize something with respect to, then we will have y1, y2, and there could be first derivative of y1, there could be second derivative of y1. We will stop there for now. Okay. So, we still have one independent variable, only x. That means that our unknowns are y1 of x and y2 of x, two unknowns. Okay. And both of them have up to first derivative only, but that can also be n derivatives. When you have two functions, what happens, right? Now, when we take variation, okay, we have the Gaussian variation. So, normally we write y and comma h, I have to write y1 comma h1 equal to 0. Sometimes we also write y1 over here to indicate that we are taking variation with respect to y1. We have to do that, and we also have to do with respect to y2. So, variation of that y2 and its variation h2 equal to 0. In other words, if I have this situation, only one independent variable x, now I have to find out from the same limits x1 to x2, I have to say that there is this function, let us say that is y1 of x, and let us say there is another function, this one let us say y2 of x, and both of these together define our integrand or our functional, right. In that case, we have to take variation of both of them, that is, I have to take a variation, that is small perturbation of y1, which we indicate with h1, okay, and this also needs a small variation, okay, that is our h2. Both of them we have to simultaneously do, but then we get two conditions because there are two functions. If there are two functions that are unknown, we need two differential equations to solve for them. Okay. So, you need two differential equations, that is what we do. So, we take one function, keep the other one constant and take the variation, that is, you take perturbation only in y1 first, then you arrive at this differential equation, then you perturb with respect to y2, then you get this differential equation. Both of these differential equations we have to solve simultaneously, because just because variation is taken with respect to y1 does not mean that this equation will have only y1, it will have y2 also. Similarly, this equation, it does not mean that it is going to have only y2, it is going to have y1 and y2. Both of these differential equations have to be simultaneously solved. Simultaneously or to be simultaneously solved. Okay. We get two differential equations, both are simultaneously solved. Okay. So, it is possible to come up with some problems, example problems where you will have two functions. We will consider one in geometry as an extension of the Brachistochrone problem. Okay. So, again when you say Gaussian variation is 0, once we have this, we know how to write Euler-Lagrange equations from it. Okay. That will be same as what we did so far when you had only that you do for y1, and you do the same thing for y2 as well. Okay. So, let us look at such a problem. Let us say I have a point here and another point over there, 2 points in a plane. So, I have a point there and a point here. Now, there is, let us say, gravity, because it is a Brachistochrone problem, right. We want to find a function for this. let us say this is x, this direction horizontal direction is x, vertical direction is y, where we have the thing. We want to find this function, let us say y1 of x somewhere, we do not know where, okay. And we have another function, let us say this is y2 of x. We have to find this y1 y2, their separation is given, okay. So, their separation along the horizontal axis is given, let us say this thing is L, okay. Their vertical heights, let us call this from some datum, this is h2, well let me put capital H2, so we do not confuse that with our variation h2, and this one let us say is h1. So, if we have this h1 and h2 and L given, we want to find these curves again, this is some curve y1, this is some curve y2, such that they both hit each other, that is at the same time. If I leave a ball at point A, let us say there is a ball here that I leave and there is a ball here that I leave, this is the ball 1 and ball 2. If I leave them at the same time, due to gravity they are going to come down, we restrict them to come down along these curves y1 and y2. At some point these two will meet, okay, some point we do not know where they will meet. At that point we want it to be the minimum time. It is a Brachistochrone problem with a little twist. Earlier problem we had only one curve, one ball, and it had to reach a certain height, but now actually this h1 h2 are just given for you and their difference is more important. So, between these two now that will be h2 minus h1 and this L, when they both are left simultaneously, when do they come, and that time has to be the least. Okay. If you consider this problem, this is Brachistochrone problem for two balls, Brachistochrone problem for two balls, balls 1 and ball 1 and ball 2. Where do they meet? We do not know. In fact, we will not be able to solve this problem based on what we have learned so far. We will come back to it, but I want to give an example of a problem where there are two functions y1 and y2, the time taken for this and time for this to be the same, because when they hit this ball, let us say would have come the way I have drawn the thing, this comes here, this comes here, they are going to hit each other there. But if you think about it, both are Brachistochrone problems, that is for ball 1 and ball 2, both are going to follow cycloids, right. That cycloid is the answer for this problem. Where they hit is what we need to find, okay. But the time taken by the balls before they hit needs to be minimized. So, if I can say minimize the time taken, okay, with respect to two functions y1 y2, okay. If y1 and y2 are different, let us say I take this point and this point, I take y1 let us say properly like a cycloid, let us say y2 I take a curve that goes something like this. When will they hit? If we are lucky, by the time this cycloid let us say goes here, okay, if the time taken for this ball to come from there to here and for this ball to take time to go to there, then they will meet over there at two balls, otherwise they actually go somewhere else, okay. It is a tricky problem, but the fact of the matter is that time taken that you want to find has to be minimum, they both have to meet at a point, and that is where this y1 and y2 are two functions that are there, okay. When you have such a thing, we will get two differential equations that are shown here from the Gattu variation, and they have to be 0. But we can pose for this problem, we cannot do right now because we have an unknown here, where they meet we do not know. We know x1 for this problem y1, but not the intermediate point. For the second one we know x2, but we do not know the starting point, right. That is why it is difficult to write as normal way that we write something to something is not possible. So, later on we will come back to this problem where we will have variable end conditions. This x1, x2 that we have, they themselves are not fixed. Okay. But for now say that we have two variables, and such things are there in structural optimization, where we can take a small problem, but only thing is that will also involve a constraint which we have not discussed, but let us take this as a motivating example to talk about constraints. So far we said minimize one functional j, but we can also consider problems such as this. Let us write that minimize j in terms of one independent variable x1, x2, f y 1 one function, another function, and then let us say first derivative of this, second derivative of that, first derivative of the second function, sorry, that can be there, and two functions y1 and y2, and let us say that there is also a constraint, okay, subject to which we are not considered so far. We can have a constraint, let us say g, which is also another functional. Okay. So, let us say that is g. So, I will use some, okay, let us call this k and call this g, let us say k, where this g, it can also be y1, y2, y1 prime, y2 prime dx. Let us say this should be equal to 0. Okay. If we have such a problem, then we have two unknown functions y1, y2, we can find it by satisfying this constraint that is given, as well as to minimize the objective function. Let us write such a problem where I would say minimize. Here we have, let us say, strain energy S E. We will take a physical problem related to structural optimization, strain energy of a one dimensional system, which we will describe, not a beam. Beam is also one dimensional system, but we will take a bar 0 to L half E A u prime square dx. Okay. So, here the variable that we have structural optimization is A of x, which is the area of cross section of a bar. So, what we are considering here is a bar, normally constant cross section bar. Let us say if it is fixed here and a force is applied, a P, you know how to calculate its deflection. That is, if this is our x, x equal to 0 here, x equal to L here, and there will be at every point some deflection, which we denote as u of x, and E is Young's modulus of the material, and this A is the area of cross section, and that needs to be found. So, this is not known, this A of x. What is A of x? At some point I can say that is the area of cross section at the location x. I have shown it to be uniform cross section, but when you are optimizing it need not be, it can have some shape like that. Okay. And that is area of cross section that we need to find at a point, that is your unknown. Okay. Now, we have now an integrand, in this case strain energy, half E A u prime square. A we do not know, u of x whose first derivative is involved here, that also we do not know, that is like this one. We have two functions, instead of y1 I have A, instead of y2 I have u. Okay. I do not have A prime, but actually I do not have u here so far, but I do have u prime and I do not have A prime. This is not there in this problem, but this is there, this is there. This will also come once we write the governing equation for this. What we want to do here in structure optimization, we want to minimize the strain energy for given volume of material, that will become this constraint, and there will be a governing equation, there will be another constraint that we will get. Okay. Let us formulate that problem, first actually explaining how we get this particular expression for strain energy. Okay. So, let us talk about that first. Strain energy of an elastic system. Strain energy of an elastic system is nothing but, if I plot stress and strain. Okay. So, this is stress, this is strain, there will be some curve, the area under this curve is our strain energy. I have deliberately drawn a nonlinear one, you can have linear one also, but whatever it is, that is the strain energy. So, if you want to write it mathematically, you would say you have to integrate, right. So, if you take a particular place here, that is the strain energy for that portion, okay. That I can take as a small thing that I accumulate. Okay. If it is linear, okay, instead of taking nonlinear that I have taken, if I take linear, that strain energy is going to be simply sigma epsilon by 2, right. Instead of taking this way, nonlinear I have to accumulate and do that. If I take it to be linear, so let us do it over there. I have sigma epsilon, if it is linear like that, area under this anywhere is going to be whatever sigma that is there at that point, whatever epsilon that I point, half of that. This is my strain energy, area under the curve, right. This is my strain energy, this is S E. Okay. But this is strain energy per unit volume, which we call strain energy density. So, this thing is actually strain energy density, strain energy density, meaning it is SE per unit volume. So, in order to get the total strain energy, I have to integrate it over the entire volume. Okay. So, what we have written here, over the entire volume of the bar, in this case we have sigma epsilon by 2 dV, right. We are taking a bar, as you can see in the figure, which is going from x equal to 0 to x equal to L of area and cross section. So, I can write this dV as A times dx. Okay. If I do that, then I can make it x going from 0 to L sigma epsilon by 2 into A dx. Why do we do that? Across area of cross section, we assume that for a bar, stress and strain are constant. That is, if I take a particular cross section that we have shown here, on that entire cross section we have sigma and epsilon the same. So, I can write that volume integration as a one dimensional integration where x varies from 0 to L, and then replace dV with A times dx. That is the small volume dV for this problem. Okay. If we also assume the stress strain relationship, that is sigma equal to Young's modulus times epsilon, then these two will lead us to 0 to L epsilon square by 2 with an E into A dx. Okay. So, what we have is EA, half EA epsilon square. What is epsilon for a bar? Epsilon for a bar, change in length du by original length dx. That is, if I take any little dx over there, this is dx, that is going to deflect by an amount du, and that is how we write the small linear strain du by dx. With all of these things, we get the strain energy of a bar as 0 to L E A by 2 epsilon square. This is u prime in our notation, u prime square dx. That is exactly what we wrote over here, half E A u prime square. Okay. That is how we get the strain energy. All right. Now, let us talk about the governing equation. So, whenever we say under a given loading, a bar has to be made as stiff as possible, meaning its strain energy is minimized to the extent possible. We also need to get that governing equation, okay, which will govern the behavior of u here. We had, if you remember, we are doing a problem where there are two functions y1, y2, or I said a and u. U right now is not restricted, but u is to be restricted because u has to be the solution as the displacement of this bar under a given loading. Okay. So, for that, let us take a bar, let this be the axis of the bar where area of cross section is varying in some fashion, which we have to find by solving a problem. Let us say this is the bar where this is our area of cross section. Let us assume that there is some loading that is given on this. Every point there is some loading, which we say is a function of x. So, p of x. Under p of x, there is also going to be a displacement. So, p of x is loading. Due to that loading, we will also have axial displacement u of x. We will have axial displacement. When you have the axial, that is what we need to find, and this axial displacement should be governed by a differential equation. See, if I give a bar, let us say it is fixed and free bar, I have loading A, I will give you Young's modulus, okay, and the total length of this. If we have that, we should be able to compute u of x. So, that should be governed by an equation, which is the static equilibrium equation. In order to find that, we can go back to our minimization of potential energy. Okay. So, for that, I would say minimize potential energy. Let us define what it is now. We have to minimize this potential energy, which is with respect to that u of x. Of all possible u of x, it is going to take particular u of x, which will minimize potential energy, that is strain energy plus work potential. Okay. This is something that we must note. The potential energy, strain energy is due to the energy stored in the bar, work potential is the applied force. We have this p of x that is going to do some work that will contribute to potential energy, and that part is defined as the negative of the work done by external forces, negative of the work done by only the external forces. Here external force is that P, external forces. Okay. So, what we have here, if we write for this problem, potential energy is strain energy plus work potential. We just derived the strain energy. Let us actually write in two different colors, so we can easily see which is which. Okay. So, let us say strain energy we already wrote 0 to L E A u prime square by 2 dx, and then work potential plus the work potential is negative of, okay, negative of the work done external force. Here the external force is P of x, and that is going to move over a distance u of x everywhere, that is going to be work potential. Together what we have potential energy is 0 to L. So, this also should be integral 0 to L dx, because at every point we have p of x, every point is going to move u of x, right. So, together we can write E a u prime square by 2 minus p u dx. That is our potential energy for a bar. Now, we need to minimize this potential energy with respect to u of x, which is 0 to L E a u prime square by 2 minus p u dx. Okay. Now, this is an integrand that depends on u and u prime. So, we can write the differential equation. So, if I call this f as a function of u and u prime, then differential equation, Euler-Lagrange equation is dou f by dou u minus dou f by dou u prime prime d by dx equal to 0. That gives us dou f by dou u is, we have this p u that gives me minus p, and then minus dou f by dou u prime gives me u E a u prime. This 2 and square 2 will both cancel, E a u prime prime equal to 0. In other words, what we got is E a u prime prime plus p is equal to 0. That is the governing equation we get. With these things, let us pose this problem that we are after now. When you have two functions, here we have a first of all, but the strain energy that we have taken 0 to L E a u prime square by 2 dx, that involves a and u, and then we have to make sure that this u is, or u prime is not something arbitrary, it has to be governed by the equation we just derived, E a u prime prime plus p is equal to 0, and then we also had this equation for the volume, that k equals 0 to L a dx minus v star is equal to 0. That is, the volume is specified for the bar, and a dx is going to give the volume of the entire bar as you change the area of cross section, that is minimum. So, now this problem, if we look at, this is dependent on two functions, okay. One is a of x and other is u of x, which is not something that we are making optimization variable. U here is called a state variable, that is, that state is the displacement, whereas a of x is the design variable in structural optimization. So, we have now formulated a problem that involves two functions, one is a design variable and is a state variable. State variable is governed by a differential equation, and there is a resource constraint which is on the volume of the bar. It is a typical structurization problem. Before we solve this, we have to discuss what happens when there is a constraint, okay, which we will consider in the next lecture, and solve this problem and then move ahead with further generalizations of the calculus of variations problems. Thank you.